This breakthrough, explored here on Agentic Era, marks a significant milestone in machine-assisted science. Researchers from Google Research, Harvard, and Carnegie Mellon University have solved a long-standing open problem in theoretical physics. By using a neuro-symbolic AI architecture, the system derived exact analytical solutions. These results remain stable where standard numerical methods fail. While highly precise, the findings are primarily constrained to asymptotic convergence. This discovery directly addresses the core friction found within the power spectrum integral. The problem centers on the power spectrum integral, specifically the calculation of the I of n, alpha term. Standard numerical integration becomes highly unstable due to singularity nodes at the poles of the sphere, where e sub 1 equals 1 and e sub 1, 2 equals -1. Analytical expansion is similarly obstructed because weight functions do not match correctly. Consequently, these instabilities necessitate a specialized neuro-symbolic engine. This architecture utilizes Gemini Deep Think as its reasoning core to overcome the earlier constraints. The engine integrates a systematic tree search with automated numerical feedback for symbolic manipulation. By employing an automated LaTeX to Python execution format, the system autonomously generates and verifies mathematical hypotheses. However, this neuro-symbolic framework is specialized for symbolic derivation tasks rather than general simulation. The engine executes its search through a specialized tree algorithm exploring 600 unique candidate nodes. Efficiency is maximized by autonomously pruning over 80% of the branches. Utilizing the PUCT strategy, the system balances predictive logic with exploration bounds. Negative prompting explicitly blocks known solutions, forcing the discovery of novel mathematical pathways. This ensures the system identifies original mathematical trajectories instead of reproducing existing literature. While the tree search explores pathways, an intermittent feedback harness provides real-time validation. The system utilizes autonomous context correction and executable Python generation to perform high-precision numerical baseline checks. By injecting error penalties through traceback analysis, it catches algebraic errors and catastrophic cancellations at machine speed. This rigorous checking ensures symbolic accuracy, though it requires a stable numerical baseline to function effectively. Correcting errors at machine speed allows for the unification of the problem's geometry over a two-sphere. All derived solutions recast the power spectrum integral into a framing involving vectors z and a. The system defines the parameter a as n times pi to simplify the integration of f sub n terms. This fundamental geometric approach provides the necessary structure for analyzing different mathematical bases, though it assumes a spherical symmetry in the initial setup. Building on this geometric framing, the AI first examined Class 1 monomial basis methods. These include the generating function approach and Gaussian integral lifting. While mathematically sound, these methods exhibit a complexity of O of n squared. They suffer from catastrophic cancellation, leading to significant numerical instability. This limitation prompted the search for more robust alternatives that could handle the increasing complexity of harmonic n without sacrificing precision. In contrast to unstable monomial methods, Class 2 spectral basis methods offer significant advantages. By applying the Funk-Hecke convolution theorem, the system developed the spectral Galerkin and spectral Volterra methods. These techniques achieve a linear complexity of order n while remaining highly stable. This shift provides an efficient path for execution, though it primarily remains a numerical or recurrence-based solution rather than a pure closed-form analytical expression. The most significant advancement comes from Method 6, known as the Gegenbauer method. By utilizing Gegenbauer polynomials as the basis, the mechanism precisely cancels the singular denominator that plagued previous attempts. This provides an exact analytic infinite series with a complexity of O of n. This method stands as the definitive analytical solution, resolving the core friction of the power spectrum integral by leveraging deep geometric properties of the two-sphere. Precision verification confirms the validity of Method 6 across diverse conditions. The AI solutions show exact alignment with benchmarks for harmonic n values ranging from 1 to 15. Plotting I of n and alpha against the loop opening angle alpha reveals consistent accuracy throughout the entire 1.5 to 3.0 radian range. This data demonstrates that the Gegenbauer method handles varying geometric parameters without losing symbolic or numerical integrity. Benchmark data further distinguishes the performance of the AI-derived methods. While Method 2 shows a steep upward error trend on a log scale, Methods 4, 5, and 6 remain consistently flat. In terms of speed, Method 6 is the most efficient, with an execution time of approximately 0.002 seconds. However, Method 5 exhibits a transient computation spike due to a matrix conditioning route, highlighting a minor trade-off in recurrence-based stability. The architectural comparison matrix summarizes the transition from instability to stable execution. Methods 1 through 3, based on monomial expansion, are hampered by O(n)² complexity and numerical cancellation. In contrast, AI-driven methods 4 through 6 achieve linear O(n) complexity. While the Galerkin and Volterra methods are numerically stable, the Gegenbauer method provides the only exact analytic solution. This shift highlights how neuro-symbolic search can identify fundamentally superior mathematical structures. This progression highlights the critical role of human-AI synergy in the discovery process. Initially, the AI generated an exact solution via an infinite tail sum of coefficients. During the human handoff phase, researchers prompted the reasoning core with intermediate tree search results. This collaboration led to an AI breakthrough where a localized recurrence structure was identified. By telescoping the infinite sum, the system established mathematical equivalence, though this specific refinement required targeted human intervention. Refining the solution allows for the derivation of the continuous asymptotic limit. This concept is essential for understanding quantum field theory massless eikonal propagators. As n approaches infinity, the function f of n approaches a limit involving delta and mass parameter terms. This provides a deep connection between symbolic AI results and fundamental particle physics. However, the exact physical interpretation depends on the specific mass scale chosen for the m²/2 term. From the asymptotic limit, the system derived the final closed-form expression for the power spectrum P sub n. This equation integrates logarithmic terms with the loop opening angle alpha to provide a clean solution for I of n and alpha as n approaches infinity. This result achieves the core goal of the project, though the complexity of the logarithmic arguments suggests that further simplification might be possible for specific physical edge cases. This derived expression confirms that modern LLMs can fundamentally accelerate scientific discovery when embedded in rigorous search algorithms. By using automated feedback frameworks, these systems autonomously navigated complex mathematical physics to identify novel solutions. This approach enables researchers to bypass traditional bottlenecks in symbolic manipulation. While this method is highly effective for derivation, its success still depends on the initial rigorous framing of the physical problem itself. This research from March 2026 demonstrates the immense potential of AI-assisted discovery in theoretical physics. Authors Michael P. Brenner, Vincent Cohen-Adad, and David P. Woodruff successfully utilized the Gemini Deep Think engine to solve an open problem. Their work, archived as Archive 2603.04735, provides exact analytical solutions that exceed traditional numerical stability. While this study focuses on the power spectrum integral, the next focus will likely involve applying these neuro-symbolic methods to broader quantum field theory challenges beyond asymptotic limits.